Hey guys, so we're back. Should be the last video for today, okay? So we're going to pick up with continuing to talk about entropy and some more qualitative ways to calculate it. We're going to pick up with quantitative ways to calculate it next class, okay? So number of microstates and the entropy tends to increase with increases in temperature, volume, and the number of independently moving molecules. So let's talk about what all that means, okay? So let's think about temperature first. So when you increase temperature, what are you doing? So temperature is a measure of the kinetic energy. And if the kinetic energy is going up, Ke equals 1/2 mv squared. So the mass isn't changing, which means the speed has to be changing. So if things are moving faster, is there going to be more randomness associated with that? Absolutely, right? Absolutely. And basically, again, we represent speeds as Boltzmann distributions. So basically what you're doing is you're broadening out the curve, you're flattening the curve, right? You're just increasing the chance that more molecules can travel at faster speeds, right? So a Boltzmann curve is basically what the government is thinking of right now when they're having us all be stuck in our homes, right? Because they're trying to flatten the curve. They're trying to take the number of cases of people getting coronavirus, and instead of having them happen a lot at once, they're trying to spread them out over a longer period of time. Because in reality, the number of people who are going to get sick are going to be the number of people who get sick. But instead of them all hitting the hospital at once and all needing like a lot of medical resources at once, we're trying to spread out when they're going to want to use those medical resources, right? So it's the same sort of spreading out that we're seeing here, right? So if there's a greater number of possible kinetic energies, then there's an increase in entropy. All right, what about volume? What's the deal with increasing the volume? Well, think about if we were going to play a game of sort of hide and seek in the HSB versus hide and seek on campus of NSU. Which one's a lot harder to play? The one on the campus, right? Because there's way more places to hide. There's more places to look, right? So an increase in volume means a great increase in the number of positions, which means the number of microstates go up, and thus the entropy goes up. All right? But we also have to consider that real particles have emotional energies as well, meaning they can move around, right? Which means we need to consider that real particles can vibrate, which means they have even greater microstates than we're thinking because we're imagining them as these sort of stationary molecules that aren't doing anything, but they are. They're constantly moving themselves, like changing their bond lengths, changing their angles. So we need to talk about that kind of stuff too. All right. So how can we define an increase in entropy? Well, an increase in entropy is an increase in the randomness or disorder of the system, or as we've been talking about more today, it's an increase in the dispersion of the energy, right? We're spreading out the energy more. So let's think about phase changes then. Well, going from a solid to a liquid, we're increasing freedom. Going from a liquid to a gas, we're increasing freedom. The more freedom something has, the more positions it can occupy, also the higher temperature, which means it's going to have higher kinetic energy, higher speeds. So there is an increase in entropy when we increase the temperature, and especially when we do a phase change, right? So if we look at this graph, so entropy's on the y-axis, temperature's on the x. Now, as we increase the temperature within a phase, entropy's going up, but not crazy dramatically. But look what happens when we do a phase change. Boom, huge entropy increase all at once because you have dramatically increased your freedom. And then look, we're heating our liquid, entropy's going up, but not too dramatically, right? And then boom, huge shoot up in entropy. And it's even bigger than the solid to liquid is the liquid to gas because you have complete freedom now. So all the entropy associated with those gas molecules. All right? But let's talk about the types of motion that molecules can undergo. All right, so what's the type of motion that molecules can undergo? Well, molecules can move, right? We call it translational motion. The motion of movement in a three-dimensional space is translational motion. So molecules can translate. They can also rotate, right? They can spin. And this spinning motion is important as well. But you have to have at least two atoms to be able to spin, right? Because imagine a ball. If you spin a ball, nothing's happening, right? So it has to have at least two atoms to change shape. All right? There are other types of motions that it can have as well. So things like a stretching motion, which is a type of vibrational motion, which is changing a bond length. So the bond length can slightly stretch out or compress in a little bit. If you have three atoms in your molecule, you can change the bond angle, which is called a bending motion. Or if you have at least four atoms in your molecule, you can have something that's called an internal rotation that allows you to change from the cis conformer, which is where the atoms are on both sides right now, to the trans right now, where they're on opposite sides. This is how molecules can hydrogen bond as well. So I want you to take these motions and think about these questions. So which type of motion contributes the most to the entropy of a substance? Which type of motion contributes the most to the entropy of a substance? And yeah, it's translational, just the ability for it to move, right? That's the most important motion. What about this question? Which type of motion is the cause of collisions? How do we hit things into each other? And yeah, again, it's translational, right? They got to be able to move. But just because two things hit doesn't mean it's effective, right? We talked about the difference between an effective collision and an ineffective collision. So how do I know for sure that I'm going to have an effective collision? We got to be able to rotate, right? We got to be able to rotate and translate. So the collision is just translational energy, but if we want to be able to make sure it's effective, we need to have rotational energies as well. All right? Now take that and add it to what we were talking about before with the different phases of matter. So think about gases. Gases have the most freedom, right? So a singular gas atom, can it translate? Can it move? Yes. Can a singular atom rotate? No, right? Can a singular atom vibrate? No. All right, what about a gas molecule? Can it translate? Yep. Can it rotate? Yep. And it can vibrate, right? What about a liquid? A liquid has limited freedom. But a singular atom should still be able to translate. But again, if it's just a singular atom, it can't rotate or vibrate. But what about a liquid molecule, like water? Well, water can translate, rotate, and vibrate. So gases and liquids seem pretty similar, right? But what about solids? So a singular solid atom, a solid, no freedom. Can it translate? No. And it can't rotate, but it can vibrate. And a solid molecule's the same way. It can't translate, it can't rotate, but it can vibrate. So what are we talking about here when we say solids vibrating? We are not talking about the things that I showed on the previous slide. We are not talking about bending or stretching or internal rotations. That's not what we're talking about. Think about what happens when you're cold. How you just going to sit, how you kind of sit in a chair and shiver. That's what we're talking about with solid vibrations. Just imagine that the molecules are just shivering. That's what a solid vibration looks like. Because unless, if we go back, whoops, sorry, going the wrong way. If we go back to this chart, ooh, it's taking more than I thought to go back. All right, oh my gosh, I forgot it was this far back. All right, if we go back to this chart, right? What's the entropy at 0 Kelvin? 0, right? That's the third law of thermo. We'll get there next lecture. But what do you notice? As soon as we're at like 1 Kelvin, the entropy is no longer 0, which means there has to be a way for solids to maintain entropy. And how they do this is they have that little shivering motion, okay? I'm just trying to get us back to where we were. All right. So what are some other changes in entropy? Well, you can dissolve something, right? So if you take table salt and you stick it in water, that table salt is going to dissociate, which means the entropy of the salt ions has dramatically increased. The water has actually lost some entropy, right? Because now it's stuck to the ions, but the amount it's lost entropy is a lot less than what it's gained from the ions. So overall, it's still going to be a favorable process. Depending upon the charges of the ions, if you had high enough charges of ions like +3s and -3s, then it might not dissolve, right? And it might not want to dissociate. And if something doesn't dissolve, remember before when I taught you the dissolution rules last semester and I said, memorize these? You probably weren't thinking about why, but this would be a why something doesn't dissolve. Because there's not a net increase in entropy. So why would it do it? It's not helpful to dissolve, so it just won't. All right? What about reactions? Sometimes reactions happen just because of the net increase in entropy. So take a look at what we have here. We have 2 moles of nitrogen monoxide reacting with 1 mole of oxygen to generate 2 moles of nitrogen dioxide. You're going from 3 moles of reactant to 2 moles of product. But you've made a 3-atom molecule, so it's got some extra vibrations in it, right? But overall, we look at this 3 things to 2 things, which means you have decreased the entropy in this system. Okay? So what's going to make the entropy of a system increase? When you perform an endothermic phase change, so you go from solid to gas, liquid to gas, or solid to liquid, when you dissolve salt with lowly charged ions, or when you increase the number of moles during a chemical reaction. So let's do some examples. So I'm going to give you a pair and you tell me which one has the greater entropy. All right, so this is your first pair. So a mole of solid sodium chloride or a mole of hydrochloric gas at 25 degrees Celsius. And it is the gas, right? And why? Because it's gas. And gases have more entropy than solids. Next, we have 2 moles of HCl gas versus 1 mole of HCl gas at the same temperature. Same molecule, so there's no difference in physical state, but you have twice as much. That's going to give you more entropy, right? Think of like having twins versus a singular kid to watch. The singular kid's easier. All right, 1 mole of HCl gas versus 1 mole of argon gas at the same temperature again. This one is comparing a molecule versus an atom. A molecule is going to have more entropy because the molecule can have the sort of stretching vibration. The atom can't have that. What about this one? 1 mole of hydrogen at STP or 1 mole of hydrogen at 100 degrees Celsius? STP, standard temperature and pressure. Standard temperature 25 degrees Celsius. So really you're comparing a different temperatures here. 25 degrees Celsius versus 100. Higher the temp, higher the entropy. And the last one. So 1 mole of hydrogen at STP, again 25 degrees Celsius, or 1 mole of SO2 at STP. So same temperature, same physical state, they're both molecules, but SO2 has 3 atoms instead of 2, so the larger molecule wins. The larger molecule has more entropy.